Hello, how's it going? Welcome back to the series. So the next task we're going to have is, at the moment, our data is hard-coded in our shader. That's not so good. Let's set things up so that we can take Vertex input. Now, this might seem a little basic, but I'm going to start off with a refresher on things, attributes, and such. So let's sort of pop in here. What are some different attributes that we could have? Well, typically, we'll want to specify a position on the screen that we're rendering to, as well as color, if we like, or texture coordinate. And there's heaps of different attributes that we can specify. Now, each of these attributes, you may remember from OpenGL, each attribute that we put in for a vertex must be between sort of 1 and 4 dimensional. So what we need to do is take this information for each vertex and somehow sort of pack it into something that our shader can read. So there's a bunch of different ways of doing this. One is what I call the human readable format. For example, if we're looking at color and position, we would specify one array for all the positions. So we'd have for point 1 the x coordinate, point 1 the y coordinate. Then we go to point 2 and we say point 2 x, point 2 y, and continue on in this way. And then similarly, we have the color, and we specify this point by point. So we have point 1 red color, point 1 green, point 1 blue, then on to point 2 red, and so on. So this is a perfectly fine way to do things. I don't quite like it because although it's human readable, it's not very machine readable. Well, it's a lot of jumping around to stitch things together. And more critically, it's sort of making two different vertex buffers. That's not my scene. So there are other ways we can do this. One way is what I call the flat representation, and that is where we have a single sort of array, and the array is populated like this. We have point 1 position in the XY, and then point 1 color in the RGB, and then we head on to point 2, so we have point 2x, and continue on from there. That's my preferred method. That's the method that I'm going to be using. But just for variety, there is another method we can use. I don't know if this is the right word for it, but I'm going to call this like a zipped layout, which is pretty similar to the flat layout. But the way this works is we have point 1 x, and then we just have all the positions. And then we go point 1 red, we have all the colors. So what's your preferred method? My preferred method is the vertices method. That's more straightforward, I would say. But anyway, we have that. Now, sort of to tie this to what we've done in the past, in OpenGL, we have vertex buffer objects and vertex array objects. So in OpenGL, we have a vertex array object, and a vertex array object holds a vertex buffer object, and it also holds the attribute pointers, which describe the data that we've just put in. The vertex buffer object has a bunch of other fields. They are basically the size and the data, the raw data, the array, is held in the vertex buffer object. And then for each attribute, we have an attribute number, we have an offset, a stride, and so on. as well as sort of number of elements for each attribute, and that's all there. Okay, very cool, very cool. So the way we deal with this stuff in Vulkan is sort of analogous to this. We have what's called a binding description. And for the binding description, we specify a binding number. So we might have, this vertex buffer is binding number 0. This storage buffer is binding number 1. This texture sampler is binding number 2, and so on. And then we have a stride, which is basically the number of bytes per vertex in total. And then we have an input rate. So is this per instance data? Is this per vertex data? And so on. So those things are sort of tied up in a binding description. And this is sort of similar to web GPU bind groups, binding group descriptions. It all sort of meshes together. Actually, I've started to understand Vulkan a lot better since I used web GPU, funnily enough. All right, and then we have, as well as that, we have various attribute descriptions. And each vertex buffer will have several attribute descriptions based on the number of attributes that it has. Each attribute description will be associated with a binding number, and that will be the same. These will match up. So if one vertex buffer has 3 different attributes and it's binding number 0, they will all be binding number 0, and they'll have their own locations, which is similar to layout location from OpenGL shaders. Okay. As well as this, we have a format. So what data are we storing, what data type, and how many elements, and the offset where that data begins. So apart from renaming these things, they are very similar. They are the same concepts. Now, another thing which is super important, have you ever noticed in OpenGL, it's weird how you can almost sort of declare pretty similar layouts between different shaders and it sort of reads them just fine? That's a happy accident. It doesn't always work that way. So what we do is when we are creating a pipeline, we specify the binding descriptions and attribute descriptions at pipeline creation. And this is thrown into it's the vertex input stage is where the shader consumes the data. So that's thrown into the vertex input info structure at pipeline creation. So if we have different pipelines which consume different sorts of data, no problem. We throw in different types of attribute descriptions and binding descriptions, and that is all good. Alrighty, so let's get this going. So the goal is to set up our binding descriptions and attribute descriptions. We'll just make a new file called mesh. In future, we'll also be sort of loading models and things, so we'll make this its own thing. Okay, now there's sort of 2 functions that I'm interested in right now. One is the binding description, and the other is the attribute descriptions for a simple sort of vec2 position, vec3 color vertex, if that makes sense. Okay, so from the Vulkan documentation, we have this field, this struct for the input binding description. It doesn't have a lot of things to make. So what we can do is we can just return one of those. Let's give it a second to fire up. Okay, so binding is 0. We're going to hard code that for now. Actually write that in. I won't be lazy. Stride is okay. We have 2 floats for position, X, Y, 3 floats for color, red, green, blue. So that's 5 floats, 4 bytes per float. We'll go with 20. Input rate will either be per vertex or per instance. And we're going to go with vertex. Instance is if we run the shader 100 times with identical data and we, sort of take new data in every instance. Now we're going to go with vertex. Okay, so that's it. We got that one very quick. So now we'll make the attribute descriptions. Again, from the documentation, we have this struct here. We have to set all of these things. Location, shader location for the layout, the binding, offset, and format. Now I'm going to return a list or a tuple, so I'm just going to sort of do this in place. Okay, so for the binding, it has to match with the above. For the location, this will be location number 0. And then for the format, so we go Vulkan, format. Things are a little strange. Even though we are working with, X and Y, the notation is standardized. So here I'm going to use 32 bits for each number, and it's going to be a signed float. So here we have signed integer, unsigned integer, and so on. That's basically what we take. I'm going to go 2 numbers, so red and green, signed float. That's just the way it is. Then for offset, that'll be 0, and there we go. That is one attribute. So then we'll make another attribute. This will be color. It will be at location 1, and it will have 3 components and an offset of 2 numbers, in other words 8 bytes into the whole thing. So we have this set up. It's looking nice enough. Now we can go to pipeline creation. This is where this information is used. We'll go import mesh, and we'll use it down here. So not in the render pass or the pipeline layout, it's down here in the vertex input. Okay, cool. So we've got those. Awesome. So we have now got one binding description. It takes a iterable object, so I'm just going to make one. And we'll go put that in there. There we are. I hate when it doesn't read things quickly. Okay, so now 2 attribute descriptions, and this is already returning a tuple, so we don't need to wrap it up in a tuple. That is fine. Awesome. So in theory, that is good. We are good to go. It's not quite that way. There is more work that we need to do. For instance, we run this right now. Yes, it works, but we're getting a whole bunch of validation errors because it's saying, hey, you need to bind a vertex buffer. Makes sense. Fair enough. So we'll get to that. Okay, so we're back because we need to investigate how to sort of make buffers. Okay, so here are my sort of research notes that I put together when I was planning this section out. So basically we have something called, where are we? If we want to create a buffer, we have this buffer create info struct, which we sort of populate the various bits. We have flags, that's fine. Size, this should be familiar. That's the number of bytes of memory that we use. Usage, 2 flags that really stood out for me, a transfer destination and vertex buffer usage. There's a whole bunch of different flags we can set there for usage. Sharing mode. So typically we'll have one graphics card, and the graphics card will be the same hunk of silicon that renders the graphics and presents them to the screen. But we might be working on a different system with multiple graphics cards or multiple different devices and things, and they might both need to share the same vertex buffer for whatever reason. So we can set whether we're going to be exclusively using one queue family, or if it's going to be owned or shared by multiple queue families. And it's said in the documentation that sharing the vertex buffer may be slower, and we can also share vertex buffers which are in exclusive mode. We just need to explicitly transfer ownership, which I guess could have some overhead. And yeah, then just the usual things. And then down here, this is a sort of structure that I'm going to go with. So I'll have our engine, and our engine will know about a vertex buffer, and that vertex buffer will be defined somewhere else. I'm calling this a triangle mesh object. The thing is, each buffer has sort of the VK buffer object and a memory object to sort of back that up. Even images, like everything, we have the object and memory sort of backing that resource up. So if we look inside the util namespace, or if you're watching this in the Python series, it's whoops, there's no namespaces, but anyway, we'll have a file in there called memory, and that memory will have a bunch of routines. We'll be able to create a buffer, find a required memory type, and then allocate memory for the buffer. And this will be interfaced with the triangle mesh. It'll call those and get the return values, and that'll be done via structs. I'll probably make a simple buffer struct with a buffer object and a buffer memory object. Yeah, there we have it. So this whole finding a memory type is non-trivial. If it were RAM, then we would just have regular, like it's sort of uniform. It's RAM is RAM. We just grab a chunk of RAM somewhere, allocate something on the heap. By the way, if you're not familiar with this, a heap is any sort of memory location where you can dynamically sort of allocate, reallocate, or free memory on the fly at runtime. But it turns out that the graphics card is not RAM. The graphics card has a whole bunch of different memory locations, a whole bunch of different heaps with different properties, different sort of visibility, different access speeds, and things like that. The classic example in Vulkan is we have memory which is host visible on the card. That's heaps which we can sort of map to via via our program. So in Python and in C++, we can map to host visible memory and send data there. But it's not the fastest. There are other heap locations which are closer to the actual graphics hardware. Those are device local, but we can't get to them directly. That'll actually be in a future video. But, in order to do any of this work, the vertex buffer that we create will have certain requirements. And that is given here by this, where are we? Get buffer memory requirements. So we make a buffer, we pass it in, we say, hey, what are the memory requirements for this buffer? And there are all these things. We have a certain size that we request, a certain alignment, and this is a big one, a certain memory type. Okay, so this is a little bit funky. I've just had to do a double take on this. My notes are actually correct. What am I even thinking? So we have memory properties that we're requesting, but as well as that, this memory requirements will tell us which types of memory, in other words, which sort of heap locations, if that makes sense, are supported by our device. So this is sort of a bit mask, and individual bits are set based on whether the corresponding memory location, memory type at that location is supported. And likewise, we can also get the physical device memory properties, and that's a sort of a struct which has a whole bunch of things. We have memory type count, fair enough, and then we have an array of memory type structs. And we have property flags. So these are the properties which are supported by each of these memory types, and a heap index as well, which would go along with these memory heaps, so the various locations of memory on the device. Okay, so what we need is, in order to allocate memory, we need to find an appropriate memory type, and in order to do that, we are going to need to have a function that sort of checks these things against each other. So we get the memory requirements, we throw that into our function, and then we check it against our physical device memory properties and get a memory type that matches. All right, so let's get into it. All right, so here we are, back into it. We'll make a new file to handle the various bits of memory allocation. We'll go do the usual. Now, we're going to sort of need to create a buffer, and I'll create all of this up front. So we'll have a simple class to hold everything that we're going to take in. Okay, so here are the basic parameters that we're going to need for all of these processes. We're going to need to know how many bytes in buffer, how many bytes of space we're requesting on our buffer, how we want to use it, and we're also, for various functions, going to need both the physical and logical devices. Okay, so we're going to populate a buffer class and output that. And yeah, so as we know, a buffer is sort of the union of two objects. We have the Vulkan buffer handle itself, as well as the memory allocation, which is backing that resource up. And actually, we can have one buffer which is backed up by several different memory locations. But anyway, so, and the next function we'll do is one to create a buffer. So just grabbing this from the documentation, we are going to need to fill in this buffer create info struct with various fields. So we can go ahead and make that. I'm going to hard code this value. I'm not going to worry about sharing buffers between queue families. All right, so cool. What we'll do is we will go ahead and make one of those buffer class instances and set the underlying buffer object by going ahead and creating a buffer. Okay, cool. So this will create the buffer. Now, what we'll need to do is return the buffer, but we will also need to allocate memory. And one of the subtasks of allocating memory is querying our device and finding the position of a memory type which matches with what we're requesting. So we'll write a function to perform that. Okay, so the first step of doing this is querying our physical device and saying what are the various memory properties of that device. So as I was saying in the section before, the memory properties, we have a whole bunch of these, a whole bunch of different memory types. We have a certain number specified here, and then in here we have an array where the actual memory properties are specified. In addition to that, before calling this, when we get the buffer requirements, that will also return an integer, supported memory indices, which is a bit field, and the corresponding bit will be set on if that memory type is supported. So go through my example. If we have a bunch of memory types and memory type 3 in this memory properties array is supported, then bit 3 will be set in this supported memory indices. If it was just bit 3, the number would just be 8, for instance, 2 to the 3. So, enough talk. Let's get these memory properties. Okay, and now let's search through each of the available memory properties. Now I'm just going to fudge this a little bit. If we fail, we still need to return something. I'm going to return 0. That's sort of a meaningless number, but hopefully it won't fail. I mean, that would be pretty sad. But anyway, so we'll go loop through the memory type count. So this will go, 0 up to whatever. So what I want to do is, let's say I equals 3. This is my example that I'm going with. So I want to check if bit 3 of this bit field is supported, of this bit mask. Now the way we can do that is we can do a bitwise AND with a number which is just the corresponding bit set to 1. So if this is 3, we take the integer of 1 and shift it 3 to the left. So that is the 32-bit integer with just 8 in there, just the third bit set. And if we do a bitwise AND the third bit is set in this number as well, then the result will be 8, because we're just picking the third bit out. And provided this is non-zero, as a boolean, it will count as true. But if supported memory indices does not have the third bit set, in my example, then the result here will be 0, because it doesn't matter that it has all the other bits. We are only caring about the third bit, and so this will fail the supported check. The next check is whether we are supporting all of the requested properties. So the way we can do this is we take memory properties, corresponding memory type of index I, and request or access the property flags, and do a bitwise AND with the requested properties. Seems a little funky. Requested properties is basically a bunch of enums packed together into a single number. So it's basically a bit mask where each corresponding bit corresponds to a certain property. And, well, if each of the properties here are supported in the corresponding property flags, then the result of applying this bit mask, it will zero out everything except for the requested properties. So if that works, it's equal to requested properties. If it fails, if one or all or whatever of these bits are not set in the memory type, then it will fail this test. Okay, so we can go if supported and sufficient, just return that type index, memory type index. And yeah, there we have it. Awesome. So that's actually not too bad. Now we have, where are we? We need to allocate memory for the buffer. Okay, so again, we'll go back through the documentation, and I guess I'm sort of giving the abridged version, but anyway. So we want to get the memory requirements for a given buffer, and it will return these fields, basically. So we can say, alrighty. Alrighty, cool. So we'll get the requirements for the buffer, Okay, and then we'll use that when we allocate the memory, because we'll need to select the given, select an appropriate memory type. Okay, cool. So the way we're using this is memory requirements will tell us how many bytes we should allocate. Wait, you say, if I allocate 20 bytes, shouldn't this be 20 bytes? And the answer is, yeah, it might be. It's also possible that due to memory alignment requirements, you might require a bit of padding, so it might be a little bit larger. That's fine too. So we also access the memory type bits. Remember, this is the system telling us, by the way, these memory types are supported. And then we put in some properties. Now I've selected two properties, host visible and host coherent. I'll sort of explain this a little bit more when I go to actually send the data in, but host visible means that it's a memory type which we can map to in our RAM. So we can sort of grab a chunk of RAM, write our data to the RAM, and the video card will direct its data bus to that chunk and grab it from there. In other words, we can think of it as just something that we can send the data natively from our program. And then this host coherent is, again, I'll go into more detail on this later, but when we write the data to the RAM and then the graphics card grabs it from the RAM, there's a bunch of other little sub-processes that go on, and if we don't use host coherent memory, we need to be more explicit about how we schedule those operations, how we synchronize those operations, so that we're not writing, we're not writing things out of order or anything like that. In other words, in layman's terms, this ensures, host visible ensures that we can write natively from our program, and host coherent ensures that when we write something, it's flushed immediately to the graphics card. Is how we can think about that. Okay, cool. So this setting up the allocation info, and then we need to actually allocate that. So I'll allocate the memory, and what do we have here? We have device. Wait a second, I'm looking at the wrong one. Okay, device, and then the allocate info. Okay, cool. So of course. How is this even going to get written into the memory? Okay, so this sort of allocates to this memory object, and then, well, so far we've created the buffer object and we've created the memory object, and these two have been independent of each other. So what we need to do is basically declare that this buffer memory is being used as the backing memory for the buffer. And yeah, we're setting the memory offset to 0 because it's going to be the single memory object for the whole buffer. If we had a really large buffer, we may not be able to allocate it all in one go. So we may split that into several smaller memory objects with several different offsets. This is fine. I'm happy with this. So we have got that. So what we'll do is sort of go up the top. And before we return the buffer, we're going to allocate some memory to it. Okay, so that's done it for now. The next stages are we're going to have to actually make a triangle mesh object and then modify the program so that it draws based on that vertex buffer. So let's get on to that. Okay, so we're almost there. We're just going to have sort of a coding marathon on the final stretch here. Now, I think I noticed a few errors in this memory.py file. If we go, where are we? Into find memory type index. Oh, okay. Maybe I just printed it wrong on my own notes. So this, in my previous notes, I had this as get physical device properties instead of memory properties. Okay, so that's all good. Now, yeah, this is going to be an issue as well. So with Python, the default is the behavior will actually return the object. It won't set it as a pointer. It's more C style. Okay, in theory, this should now be looking okay. All right, so one thing I'm going to do is I'm just going to edit the shader compilation and the vertex, don't do that, and the vertex shader. So for the shader, I'm going to get rid of all of this stuff, and I'm going to specify the input as attributes. And I'll go ahead and use them down here. So I'll set the position and the color. Okay, good. Now I'll just go and compile this. Oh wait, I messed something up. So I changed my Vulkan version recently, so just make sure this is up to date. Okay, and now this should be all right. So I'm going to go, there we have it. Awesome. That's compiled with no errors. And check over here, the dates have changed. So that's all good. Okay, so the shader side should be fine. Now I'm just going to make a new file called triangle mesh. And this is where I will, so triangle mesh will basically declare the vertex buffer and manage it. And then that will be used in, where are we? The engine will use that as one of its assets. And then we'll run the main function and see how it goes. I'm lazy, so I'll just copy that in. So yeah, here the first two numbers are the XY position and the last three numbers are the color. So my test, this will be the same sort of triangle, but my test will be, is it green? Because these are all green colors. Vertices will be a temporary variable because we're just going to use it once to send the data over, and then the data will exist on the graphics card. Okay, cool. So we're just setting things up, we're running it. This will jump into the memory file, create the buffer, allocate the memory for it, and yeah, that's done. Now all we need to do is find a way to get the data from this variable, this array, into the vertex buffer. So like I was saying before, Vulkan has a chunk of RAM that it looks at, and we ask Vulkan, hey, I want to allocate space to this this object, this memory object. Where in RAM should I write that? It tells us, then we send the data there, and then it sort of copies it over to itself. So we need to get the memory location, and we do that with Vulkan map memory. It takes a few arguments. So we need the device, the memory that we're mapping. So remember, we have the vertex buffer, and then inside that we have the buffer memory object. That's the one that we're looking for. Then we have the, where are we? The offset, which is 0 because we're going to start from the beginning. And then we have the size, which is the number of bytes that we are writing. And I believe it will also complain if we don't set flags, so we'll set the flags to 0. No special flags are being set. So remember, let's have a look here. So I think we have 15, yeah, that's right. We have 15 numbers and then 4 bytes per number, so 60 bytes. But for instance, it would be more common if, due to padding requirements, we had to allocate 64 bytes. But that's fine, because what we would do is we would still write the first 60 bytes. We would still have to do that. So we don't need to worry about the size which has actually been allocated to this buffer, because when we got the memory requirements, it sort of guaranteed that we would always be at least the correct size. It may be the correct size plus a bit of padding. It's not anything to worry about. So where was I? Now we need to get a way to move the data from the vertices variable into this memory location. It turns out we have a function called memmove. I think if we go over to config, let's just see how this goes. We go in Vulkan. What's this FFI? So yeah, Vulkan cache. So this is sort of auto-generated. I wonder if we can find memmove. We can't. Let's just assume it's there. So this is sort of comes from the Vulkan backend, parsing the vulkan.h files, as well as I think running a little custom script or something. It basically gets a bunch of functions from the C environment. Anyway, long story short, we have a memory move function. That's good. So we move to memory location. Where are we? Move to memory location. The data we move is the data in the vertices variable, and the size of data that we are moving is the number of bytes in the vertices variable. There we go. Okay, cool. So remember, when we get a mapped range for an object, Vulkan sort of has some overhead in there, or at the very least has a requirement that we can only map so many things at once. So it's a good practice to sort of unmap after we've mapped. I think I said this in a previous thing, but basically I believe it's fairly likely that it actually sets up an asynchronous interrupt routine to monitor that memory location, and if it's changed, then to trigger the data bus to take the memory over, which has some overhead. So anyway, I'll stop rambling. We need to unmap that memory. Okay, that's looking good. And the last thing we need to define is the destroy function, which will free the memory. And this is the reason that I stored the logical device, because the logical device will be used in the memory freeing operations. Okay, cool. So there we have it. Just give it a second to get rid of that error. What are you doing? There we go. Okay, awesome. So now we can go to the engine and set it up so that it has this triangle mesh. So we'll just import that. And running from top to bottom, after we have set up everything that we'll need, we will go ahead and make the assets. Okay, so just define that function down below. Okay, cool. So at the moment, it's very simple. You can imagine that with time, these functions will be becoming more complicated. So the next thing I'm going to make is a function to prepare the scene for rendering. And all it's really going to do is bind the vertex buffer. It's not just self that it's going to take. I'm also going to take command buffer to record that operation on. So yeah, because this is called bind vertex buffers, it has the option of putting in basically a list of buffers. But here we're just doing one, binding it at binding index 0, and just one of them. Okay, awesome. So we've got that. Now we'll go down to record draw commands, and just before we start actually drawing things, we will prepare the scene. Cool. So as you can imagine, again, this prepare scene function will also be becoming more complicated as features are added. So that's looking good. We can go right down to the bottom to the cleanup function. And we have all of this stuff. Then here we're destroying the device. The triangle mesh is going to use the device to call its destroyers. So it's probably a good idea to clean it up before destroying the device. Give that a second. Okay, good. Yep, recognizes that function. Let's give this a shot, see if there's anything that I missed. So annoying. Okay, what are you complaining about? Memory line 1. Okay. Oh yeah, no, don't do that. What's wrong? Must have automatically filled that line in. Okay, cool. So here we have it. So we have pretty much the same thing as before, except now the triangles are under our control. It's data that we are passing in ourselves, and just as before, we can resize it. That works just fine. And there we have it. So there it is. Hope you enjoyed that session. It's a bit of a marathon, but we got there in the end. And yeah, have a good one. I'll see you soon. All right. Bye.